Hello, my name is Beau. My classmate Brooke Johnson and I decided to take on a project around natural language processing for COVID-19 research as our final project for Big Data Health. Our motivation for this project came from a call to action issued by the White House on March 16, 2020, for the data science community to try to help healthcare professionals battling the very active COVID-19 crisis. Through a collaboration with many other institutions, the COVID-19 Open Research Dataset, or CORD-19, was created. In addition to the open source dataset, a number of key questions about the COVID-19 virus were also released as part of this call to action. We set out to build a closed domain question answering system using the CORD-19 dataset. The CORD-19 dataset is a corpus of over 57,000 scholarly articles related to the group of coronaviruses that include the very active COVID-19 virus, the SARS virus, and others. We broke our project up into 4 different goals. The first goal was to build an ETL pipeline that would be able to efficiently load and clean the thousands of articles that make up the corpus. The size of the data, which was multiple gigabytes, presented a challenge to us. Luckily, we learned a lot about big data frameworks this semester, so we were able to utilize them to accomplish this goal. More to come on that. The second goal was to build NLP models based on the clean data. The third goal was to use these models to answer the questions generated by the user of our software. And the final goal was to clearly present the best answers generated by our models to the user. Here's an overall architecture that we came up with in order to transform the raw corpus of articles into answers of questions passed in by the user. I will now step through this in more detail. The first step in our software architecture is to read in and process the individual raw articles in the corpus. As I mentioned, the corpus consists of thousands of articles totaling multiple gigabytes of data. In order to handle this data and also allow for additional data to be added in the future, we used PySpark to read in the data and process it using its distributed framework. The processing of the data was consistent with typical NLP pre-processing and included word tokenizing, removing stop words, removing punctuation, and lemmatizing. Again, all of this pre-processing was done using PySpark to make the handling of the massive amount of data more efficient. Once the data was cleaned, we then passed it along to a TF-IDF model that we created using the library NLTK. TF-IDF stands for Term Frequency Inverse Document Frequency, and it serves as a measure of how frequently a word appears in a single document versus the entire corpus of documents, and is intended to show how important a word is to a single document, and therefore how much weight it should be given by the model. Both the TF-IDF model and the question asked by the user are then passed to a similarity detector that we created using the library GenSim. The similarity detector assigns a score to each document using the cosine similarity and representing how similar the document is to the question asked based on the TF-IDF model. From here, we select the top N, typically the top 10 documents ranked by similarity, to pass into the next part of our architecture. Briefly, I wanted to show the power of pre-processing the data so that it would be cleaned before going into the TF-IDF model. As shown here, the top 10 documents found using the previous step were found to have a higher similarity in every case when they were cleaned versus unclean. The final section of our architecture uses a pre-trained deep learning language representation model created by Google called BERT. BERT is able to serve many purposes, but we are specifically using its question and answer functionality. Given a question and a sentence of context, BERT will return the most likely answer to the question within the context, along with a measure of confidence that it has found the right answer. BERT is a very powerful model and can take a good amount of time to run, which is why we didn't choose to just run it over every sentence in the corpus of documents. We pass every sentence from the top 10 articles into the BERT model and retrieve the top 10 answers based on the measure of confidence. We chose to display the top 10 most likely answers to the user's question in an HTML format that makes it both easy to read and share with others. This is an example where the user asked, "What drugs are being used to successfully treat the COVID-19 coronavirus?" For each of the top 10 answers, of which 2 are shown here, we display the score generated by the BERT model, the title of the document where this answer was found, the published date of the article, the short answer that BERT determined to be the likely answer, and finally, the full paragraph of context. As you can see here, in both of the top 2 answers, BERT found a handful of drugs that articles mention as being used to treat COVID-19, and you can see the context of how they're being used in the full paragraph text. In order to analyze the results of our system, we selected at random the 10 questions shown here from the list of key questions asked in the call to action by the White House. Analyzing question answering systems can be a challenge, especially closed domain question answering systems for which there are no classified answers. For each of these 10 questions, we took the top 10 answers generated by our system as selected answers, and then took a random sample of the remaining answers that were not selected as the unselected answers. By analyzing the selected and unselected answers, we were able to generate scores of accuracy, precision, recall, and F1 for each question. For question answering systems, accuracy shows how well a question is answered relative to other questions. Precision shows us how well our system is at presenting only correct answers. Recall shows us how well the system selects all true answers in the corpus. And F1 shows us the trade-off between the precision and recall. Each of these measures is important in analyzing our system for different reasons. 9 out of 10 of the randomly selected questions scored over 50% for all metrics, which we conclude to be a good measure for the usefulness of our project. The software that we built was able to accurately provide answers to 9 out of 10 randomly selected questions that came directly from the White House and its partner institutions. In the process of building this tool, we became more familiar with NLP techniques, the state-of-the-art language representation model, BERT, and big data tools like Spark. These are all very powerful tools for solving real-world problems that involve large, unstructured data. Brooke and I both thank you all for a great semester.